Welcome to Sleepy Stories. In this episode, we will take a clear and steady look at how Earth slowly changes. The purpose of this story is simple. It is meant to help you learn something real and grounded about the world while allowing your body and mind to rest. You do not need to concentrate intensely, and you do not need to stay awake to the end. If sleep comes quickly, that is completely fine. If it does not, that is also completely fine. You may simply listen and allow the information to unfold at its own pace. Before we continue, if you enjoy stories like this, you can like and subscribe to Sleepy Stories, so these calm explanations are always easy to find again. For now, you can settle in, let your breathing slow, and allow your attention to soften. When most people look at Earth, it feels solid, fixed, and finished. Mountains seem permanent, oceans appear stable, the ground beneath your feet feels still. On the timescale of a single day, a year, or even a lifetime, Earth gives the impression of being unchanging. Yet this impression is misleading. Beneath that apparent stillness, Earth is constantly moving, adjusting, and reshaping itself. The changes are rarely fast enough to notice in daily life, but they never stop. Earth is not a static object. It is an active system. Rock flows slowly deep below the surface. Continents drift apart and come together. Mountains rise while wind and water wear them down. Oceans advance and retreat. Climate shifts over long periods, influencing where forests grow and where deserts form. None of this happens suddenly in most cases. Instead, it unfolds gradually, over thousands and millions of years. Understanding Earth requires stepping away from human expectations of speed. Many of the planet's most important processes move so slowly that they feel invisible. A mountain range may rise by a small amount each year, far less than the thickness of a sheet of paper. A continent may travel only a few centimeters in the same time. Rivers may remove only a tiny grain of rock at a time. Yet when these small movements continue without stopping, the result is dramatic change. This story is about those slow processes. It is not about disasters or dramatic moments. It is about the quiet forces that shape Earth day after day, even when nothing seems to be happening. By looking at these slow changes, it becomes easier to see Earth not as a finished world, but as one that is always becoming something slightly different. Earth has been changing since the moment it formed. From its earliest days, heat, gravity, and motion shaped its structure. That energy did not disappear once the planet cooled on the surface. Much of it remains trapped inside, driving movement deep below the crust. Even now, long after Earth's formation, that internal energy continues to influence everything above it. The surface we live on is thin compared to the planet's full size. Beneath it lies a vast interior that moves at a pace far slower than weather or seasons. Solid rock, under enough heat and pressure, can behave like a very thick fluid, flowing over immense spans of time. This slow motion pushes continents apart, presses them together, and slowly rearranges the surface of the planet. From space, Earth may look calm and complete. From the perspective of deep time, it is never still. Coastlines shift, seas open and close. Life adapts, spreads, and sometimes fades away. The planet does not aim to stay the same. It responds continuously to forces acting within it and upon it. As you listen, there is no need to hold every detail in mind. The goal is not memorization, it is familiarity. The ideas may come and go, just as the planet itself changes gradually, without urgency. You may notice your breathing slow as the pace of the story remains steady. That is natural. The subject itself invites patience. Over the course of this story, we will move slowly through the ways Earth changes. We will look beneath the surface, across the oceans, and through long stretches of time. Each idea builds gently on the last, without rushing toward conclusions. Earth's story is not one of sudden transformation, but of constant motion that rarely draws attention to itself. For now, you can simply listen. Earth has been changing for billions of years, and it will continue to change long after any single moment has passed. There is no need to hurry. To understand how Earth changes, it helps to begin with time itself. Human experience is shaped by short intervals. A day feels long, a year feels significant. A lifetime can seem vast when measured from beginning to end. Within these spans, most of Earth appears unchanged. Hills look the same. Coastlines seem fixed. The position of continents does not shift in any visible way. This creates the impression that Earth is stable and largely complete. Earth, however, operates on very different clocks. Many of its most important processes unfold across thousands, millions, or even billions of years. When change is spread across such long intervals, it becomes difficult to notice from one moment to the next. The absence of visible motion does not mean nothing is happening. It only means that the movement is slow compared to the pace of human attention. Geological time is measured in layers, not moments. A mountain range does not rise in a single event. It grows gradually as forces deep within the planet push rock upward year after year. At the same time, wind, rain, and ice begin wearing that rock away. The mountain may be gaining height and losing material at the same time. Both processes happen slowly, yet neither ever stops. When observed over enough time, entire landscapes can be transformed. The same is true for oceans. Seas open as continents drift apart, allowing water to fill new spaces. Over long periods, those oceans can close again as continents slowly move back toward one another. From a human perspective, oceans appear permanent. From a geological perspective, they are temporary features, appearing and disappearing as the surface of the planet rearranges itself. Earthquakes and volcanic eruptions often draw attention because they happen quickly. They feel sudden and dramatic, yet even these events are expressions of slow change. An earthquake releases stress that may have been building for centuries. A volcanic eruption releases material that has been moving upward through the planet over very long periods. The visible event is brief, but the process behind it is extended and continuous. When thinking in geological time, speed takes on a different meaning. A continent may move only a few centimeters in a year. This is slower than walking, slower than growing plants, slower than most daily activity. Yet when that movement continues for millions of years, continents can travel thousands of kilometers. Oceans can form where land once existed. Mountains can rise where flat plains once stretched. Rivers provide another clear example. In a single day, a river may carry only a small amount of sediment. The change to its banks may be almost impossible to see. Over centuries, however, rivers can carve valleys, shift their courses, and reshape entire regions. Over longer spans, they can cut deep canyons and transport vast amounts of rock from mountains to the sea. The river never needs to rush. It only needs to keep moving. Because human lives are short relative to these processes, it is natural to underestimate their power. Slow change can feel insignificant simply because it does not demand immediate attention. Yet, in Earth's history, slow change has shaped nearly everything that exists on the surface today. The arrangement of continents, the height of mountains, the depth of oceans, and the distribution of ecosystems are all the result of persistent motion rather than sudden creation. Learning to think in longer timescales requires patience. It means letting go of the expectation that change must be fast to matter. On Earth, some of the most influential forces are those that act quietly and continuously. They do not announce themselves. They do not hurry. They simply persist. As this story continues, time will stretch further. Moments will give way to eras, and small movements will accumulate into large transformations. Nothing needs to be forced or resolved quickly. Earth's history shows that lasting change does not depend on speed. It depends on continuity. Earth's slow changes begin long before continents, oceans, or life appeared on its surface. To understand why the planet is still changing today, it helps to look back to how it first came into being. Earth did not form suddenly or cleanly. It emerged gradually from a vast cloud of dust, gas, and rocky material orbiting a young sun. Over time, gravity pulled these particles together. Small pieces collided and stuck, becoming larger bodies. Those bodies collided again, slowly growing into something more solid and more complex. This process took a very long time. There was no single moment when Earth became a finished planet. Instead, it passed through stages. With each collision, energy was released as heat. As Earth grew larger, its gravity strengthened, pulling in more material and generating even more heat. The early planet was warm throughout, not just on the surface, but deep inside as well. As heat built up, materials within Earth began to separate by density. Heavier elements, such as iron, slowly sank toward the center. Lighter materials remained closer to the surface. This gradual sorting created layers that still define Earth today. The deepest regions became extremely hot and dense. Above them formed layers that could slowly move under pressure. At the surface, a thin outer shell cooled enough to become solid. Even after Earth's surface cooled, the planet did not lose its internal energy. Much of the heat generated during formation became trapped inside. Additional heat continued to be produced by the slow decay of radioactive elements within the planet. This meant that Earth never truly became cold or inactive. Instead, it carried a long-lasting internal warmth that continues to shape its behavior. In the earliest periods of Earth's history, the surface was unstable and constantly changing. There were no permanent oceans at first. Water existed mainly as vapor in the atmosphere. Over time, as the surface cooled further, that vapor condensed and fell as rain. Gradually, water collected in low areas, forming the first oceans. This did not happen all at once. It unfolded slowly as conditions allowed. The atmosphere also changed gradually. Gases released from Earth's interior accumulated over long periods. The composition of the air shifted as volcanic activity continued and, much later, as life began to influence the environment. Each of these changes depended on processes that moved slowly and steadily rather than quickly or dramatically. What matters most is that Earth has never been static. From the moment it began to form, motion and adjustment were built into the planet itself. Heat moved from one region to another, materials shifted position, layers developed and interacted. These processes did not end once Earth looked familiar. They continued, quietly and persistently. Even today, Earth still carries the consequences of its formation. The heat trapped inside the planet continues to move upward. Dense materials remain deep below, while lighter materials stay closer to the surface. This internal structure is not a relic of the past. It is an active system that influences everything above it. When continents drift, when mountains slowly rise, and when oceans gradually change shape, these are not new behaviors. They are extensions of patterns that began billions of years ago. The planet did not settle into stillness after its early history. It simply slowed to a pace that is difficult for human senses to perceive. As you listen, there is no need to hold the entire history of Earth in mind. The key idea is simple and steady. Earth was never finished, and it never stopped adjusting. The slow changes we observe today are part of a continuous process that began with the planet's formation and continues without interruption. The past is not gone. It remains active beneath the surface, guiding the motion that shapes Earth quietly, patiently, and without pause. To understand how Earth continues to change long after its formation, it is necessary to move slowly beneath the surface and consider what lies below the ground we experience every day. The planet is not made of a single solid mass. It is structured in layers, each with distinct properties and roles. These layers interact continuously, allowing motion and change to persist even when the surface appears calm and unmoving. At the center of Earth lies the core, a region of extreme heat and pressure. This heat is not the result of surface conditions or recent events. It comes from two long-lasting sources. One is the leftover energy from Earth's formation, stored deep within the planet. The other is the slow decay of radioactive elements, which continues to generate heat even now. Together, these sources ensure that Earth's interior remains warm and active. Surrounding the core is the mantle, a vast layer that makes up most of Earth's volume. Although the mantle is solid rock, it does not behave like the rigid stone found at the surface. Under immense heat and pressure, mantle rock can slowly deform. It can bend, stretch, and flow, but only over very long periods of time. This movement is extremely slow, far beyond the scale of human observation, yet it is constant. Heat within the mantle moves gradually upward. warmer material becomes slightly less dense and rises, while cooler material sinks. This slow circulation transfers energy from deep within Earth toward the surface. It does not surge or rush. It unfolds patiently, maintaining internal motion over millions and billions of years. Because heat is released slowly rather than all at once, Earth remains geologically active rather than cooling into stillness. Above the mantle lies the crust, a thin outer layer compared to the planet's full size. This is the layer where continents, oceans, and life exist. The crust may feel solid and stable, but it rests on the slowly moving mantle below. It is not fixed in place. Over long spans of time, it responds to the motion beneath it, shifting position and adjusting its shape. This connection between Earth's deep interior and its surface is continuous and unavoidable. Changes below influence what happens above. Pressure deep within the planet contributes to the slow movement of surface material. Heat rising from the interior affects where new crust forms and where old crust is recycled. Even the most stable-looking landscapes are supported by processes that never fully stop. Because these movements are so slow, they are easy to overlook. The ground does not tremble, the horizon does not shift, yet beneath this stillness, material is always adjusting. The surface we inhabit is the result of countless small motions accumulated over immense spans of time. Earth's layered structure allows change to persist without chaos. Each layer plays its part, transferring energy, redistributing material, and maintaining balance. Past conditions influence present motion, and present motion shapes future change. Nothing within the planet exists in isolation. As you listen, there is no need to visualize every layer in detail. What matters is the relationship between them. Earth's surface is supported by slow, steady motion below, and that motion provides the foundation for everything that changes above it. From this quiet internal activity emerge the larger patterns that continue to reshape the planet, patiently and without urgency. The slow movement deep within Earth becomes visible at the surface through a process known as plate tectonics. Although the ground beneath your feet may feel solid and unmoving, the outer layer of the planet is not a single, continuous shell. Instead, it is divided into large sections called plates. These plates rest on the slowly moving mantle below and drift gradually across it, guided by forces that operate far beneath the surface. The motion of these plates is extremely slow. In many places, they move at a pace comparable to the growth of fingernails. From one year to the next, this movement is impossible to notice. Maps remain accurate, coastlines appear unchanged, cities stay where they are, yet the key feature of plate motion is not speed, but persistence. The plates do not stop moving. Over millions of years, even the smallest movements accumulate into profound changes. As plates drift apart, gaps open in the crust. Material from below rises to fill these spaces, cools, and forms new crust. This process gradually creates new sections of ocean floor. Over time, entire oceans can open between continents that were once joined. This separation happens slowly and steadily, without a single moment of division. What appears today as a vast ocean basin began as a narrow zone of gradual spreading. In other regions, plates move toward one another. When this happens, the crust can thicken and rise, contributing to the formation of mountain ranges. In some cases, one plate is forced beneath another and slowly recycled back into the mantle. This process removes old surface material and returns it to Earth's interior, where it becomes part of the planet's long-term circulation. Again, none of this happens quickly. These changes unfold over spans of time that exceed human experience. Plate boundaries are places where stress builds slowly. Plates press, pull, or slide past one another, often held in place by friction. For long periods, there may be no visible change at all. Yet beneath the surface, energy continues to accumulate. The surface expression of this stress may come much later, but the underlying movement never truly pauses. Plate tectonics provides a quiet framework for understanding Earth's surface. It explains why continents have their current shapes, why certain regions are mountainous while others are flat, and why oceans exist where they do. These patterns are not accidental. They are the outcome of slow, organized motion acting continuously over immense spans of time. Thinking of continents as fixed objects can make Earth seem static. Thinking of them as travelers reveals a different picture. Land masses assemble, break apart, and rearrange themselves again and again. The ground beneath your feet has followed a long journey, even if it feels stable in the present moment. As this slow movement continues, it sets the stage for many other processes. Mountains rise and are later worn down. Oceans expand and change shape. The surface of Earth is never finished. It is constantly revised by motion that rarely demands attention, yet quietly shapes the planet more thoroughly than any sudden event. For most of the time, Earth's slow movement remains unnoticed. The ground beneath your feet feels firm and dependable. The horizon looks steady. Nothing seems to shift or change. Yet beneath this apparent stillness, motion continues without interruption. Plates press against one another, slide past each other, or slowly pull apart. This movement is quiet and persistent, building tension gradually over long periods of time. An earthquake does not begin when the ground starts to shake. It begins much earlier, often decades or centuries before. As tectonic plates move, friction can cause them to lock together. While they remain stuck, motion does not stop. Instead, stress accumulates. Rock bends slightly under pressure. Energy is stored quietly within the crust. This process continues patiently, without visible signs, until the built-up stress exceeds what the rock can hold. When that point is reached, the stored energy is released. The plates slip, sometimes by only a small amount, yet the effect can be felt across wide areas. The shaking that follows may last only moments, but it represents the release of energy that has been gathering slowly for a very long time. In this way, even sudden earthquakes are expressions of gradual change rather than abrupt beginnings. Volcanic activity follows a similar pattern. Deep within Earth, heat causes rock to melt and become less dense than the surrounding material. This molten rock does not rush upward. It moves slowly, finding pathways through cracks and weak zones in the crust. Over long periods, pressure builds beneath the surface as molten material accumulates. Most of this movement remains hidden, taking place far below where it can be observed. When an eruption occurs, it may appear dramatic, but it is not sudden in origin. It is the final stage of a process that has been unfolding quietly over thousands of years. The surface expression is brief compared to the long preparation that precedes it. Once the pressure is released, the system settles again, returning to its slow and steady rhythm. These moments of release often capture attention because they interrupt the illusion of stillness. They can feel disruptive or powerful, yet they are rare compared to the vast stretches of time during which Earth adjusts itself silently. For every moment of visible change, there are countless years of slow motion that pass without notice. Understanding this context helps place such events within Earth's broader behavior. They are not signs of instability or disorder. They are part of a balancing process in which energy builds and is released over time. The planet does not hurry these adjustments. It allows pressure to accumulate naturally and resolves it only when necessary. As you listen, there is no need to focus on the dramatic aspects of these events. The deeper pattern is the quiet build-up that surrounds them. Earth spends far more time preparing for change than displaying it. This steady preparation reflects the planet's preference for continuity rather than urgency. If your attention drifts or your breathing slows, that is completely fine. Just as Earth releases energy only when conditions require it, your mind does not need to remain alert at every moment. The motion continues whether it is noticed or not. When the ground settles again, the slow movement resumes, shaping the planet patiently and without pause. Mountains often give the impression of permanence. Their height, mass, and solid appearance suggest stability and endurance. From a human perspective, they seem unchanged from one generation to the next. Yet mountains are not fixed features of Earth's surface. They are among the clearest examples of how slow processes shape the planet continuously, lifting land upward while other forces work just as steadily to wear it down. Mountain building begins deep below the surface, where tectonic plates interact. When plates move toward one another, the crust can be compressed and thickened. Over long periods of time, this thickened crust is pushed upward, raising the land above it. This motion is extremely slow. In a single year, the increase in height may be far smaller than the thickness of a leaf, yet the movement does not stop. Given millions of years, even such small upward motion can produce vast mountain ranges. At the same time that mountains rise, erosion immediately begins to act on them. Wind removes fine particles from exposed surfaces. Rainwater flows across rock, slowly loosening and carrying away material. Rivers carve channels that deepen gradually as water follows gravity. In colder regions, ice expands in small cracks, widening them over repeated cycles. Gravity pulls loosened material downhill, redistributing it across the landscape. Because uplift and erosion occur together, a mountain is never complete. It is always in transition. Some mountain ranges rise faster than erosion can reduce them, at least for a time. Others are worn down more quickly than they are lifted, gradually losing height. Over very long spans of time, even the tallest peaks can be lowered until they blend into surrounding terrain. This balance explains why Earth's mountains vary so widely in shape and appearance. Sharp, jagged peaks often indicate relatively recent uplift, where erosion has not yet had time to soften the landscape. Rounded hills and broad plateaus suggest older mountain systems that have been exposed to erosion for much longer. These differences reflect time rather than strength or stability. Seen this way, mountains are not monuments frozen in place. They are temporary expressions of deeper forces at work beneath the surface. Their rise and decline record the slow interaction between internal motion and surface processes. Each ridge and valley is shaped by patience rather than speed. As you listen, there is no need to imagine dramatic change. The key idea is continuity. Mountains rise quietly and are worn down just as quietly. The same steady forces that created them continue to reshape them, grain by grain, year after year, without urgency or pause. Erosion is one of the most persistent forces shaping Earth's surface. It does not act suddenly or dramatically. Instead, it works quietly, removing small amounts of material over long periods of time. Because its effects are subtle from one moment to the next, erosion often goes unnoticed. Yet when allowed to continue without interruption, it can transform entire landscapes. Water is one of erosion's most effective agents. Rain falls onto rock and soil, sometimes gently and sometimes steadily. As it moves across the surface, it carries tiny particles with it. Over time, these particles are transported downhill, away from higher ground. Streams form as water gathers, and streams merge into rivers that carry sediment across vast distances. Each movement removes only a small amount of material, but the process never truly stops. Rivers deepen their channels slowly, responding to gravity and the shape of the land. As they flow, they cut into rock and soil, shaping valleys that become wider and deeper over long periods. Even where water appears calm, it is still doing work. The power of a river lies not in speed, but in persistence. Given enough time, flowing water can reshape solid rock. Wind contributes to erosion as well, especially in dry or open regions. It lifts fine grains of sand and dust from exposed surfaces and carries them elsewhere. Over time, this action smooths rock faces and redistributes sediment across wide areas. Ice plays its role in colder environments. Glaciers move slowly across the land, grinding rock beneath them and carrying material far from its original location. When the ice melts, it leaves behind landscapes shaped by long, steady movement. Chemical processes add another layer to erosion. Water reacts with minerals in rock, gradually weakening them. Temperature changes cause expansion and contraction, opening small cracks that grow wider over repeated cycles. These processes work quietly, breaking rock into smaller pieces that are more easily transported by wind or water. Erosion does not act alone. It works alongside uplift, tectonic movement, and climate. As mountains rise, erosion begins to lower them. As land is worn down in one place, sediment is deposited in another. Material removed from high regions is carried to plains, deltas, and ocean floors, where it becomes part of new landscapes. Over thousands and millions of years, this steady redistribution reshapes continents. Sharp edges become rounded, high ground is reduced, low areas fill in. The surface of Earth records these changes in layers, curves, and textures that reflect long histories of patient adjustment. As you listen, there is no need to focus on motion or force. Erosion works without urgency. It does not hurry, and it does not pause. It simply continues, shaping the land grain by grain, maintaining Earth's slow rhythm of change. Rivers are among the most patient and persistent shapers of Earth's surface. At first glance, a river may appear calm, even familiar. Its course may seem fixed, its banks stable. Yet a river is always moving material, always responding to gravity, and always adjusting its path in subtle ways. From high ground to low ground, rivers connect landscapes and quietly reshape them over long periods of time. Every river begins with small movements of water. Rain falls on hills, mountains, or plains, and starts to flow downhill. These small flows gather into streams, and streams combine to form rivers. As water moves, it carries particles of soil, sand, and rock with it. Each particle represents a tiny change to the land it came from. Over a single day, this change is nearly impossible to detect. Over centuries and longer spans of time, the effect becomes significant. As rivers flow, they cut into the land beneath them. The force involved is not sudden or violent, it is steady. Water follows the path of least resistance, gradually deepening channels and widening valleys. When the land rises slowly due to tectonic forces, rivers respond by cutting downward, maintaining their course over time. When land sinks or sea levels rise, rivers slow and begin to deposit sediment instead of removing it. This balance between erosion and deposition allows rivers to build as well as carve. Floodplains form as rivers overflow their banks during periods of high water, spreading fine sediment across wide areas. Over long periods, these deposits create fertile soils and flat landscapes. At river mouths, where flowing water meets the stillness of the sea, deltas form. Layer by layer, sediment settles and builds new land outward into the ocean. Rivers do not remain fixed in place. Their channels shift gradually as sediment is deposited on one bank and removed from another. Meanders grow wider over time. Entire river paths can slowly migrate across landscapes, leaving behind curved scars that mark earlier courses. These changes happen quietly, guided by water speed, sediment load, and the shape of the land. Even the largest canyons on Earth owe their existence to rivers that worked patiently over immense spans of time. The water that carved them did not need to rush. It only needed to continue flowing. Given enough time, even solid rock yields to steady movement. Rivers link distant parts of the planet. Material eroded from mountains may travel hundreds or thousands of kilometers before settling. In this way, rivers carry the history of high places to low ones, redistributing Earth's surface slowly and continuously. As you listen, there is no need to imagine rushing water or dramatic scenes. The defining quality of rivers is persistence. They move without urgency, adjusting their course as conditions change. Through steady motion rather than force, rivers help shape continents, one grain at a time, maintaining Earth's long rhythm of gradual change. Coastlines often feel like clear boundaries. On maps, they appear as sharp lines separating land from sea. In daily experience, they seem stable and familiar. Beaches, cliffs, and shorelines appear to hold their shape over long periods. Yet coastlines are among the most changeable features on Earth. They are not fixed edges, but shifting zones shaped by the slow interaction between land, water, and time. The position of a coastline depends on many factors. Sea level plays an important role, rising and falling over long periods as climate changes and ice accumulates or melts. At the same time, the land itself can rise or sink due to tectonic forces beneath the surface. When land slowly lifts, coastlines move outward. When land subsides, the sea advances inland. These changes happen gradually, often unnoticed within a human lifetime. Waves continuously reshape the edges of continents, Each wave removes or redistributes small amounts of material. Sand is carried along the shore, cliffs are slowly worn down, and rock fragments are broken into finer particles. The energy involved is not constant. Storms may accelerate erosion for short periods, but the long-term shape of a coastline is determined by countless ordinary waves acting over extended spans of time. Rivers also influence coastlines by delivering sediment to the sea. Material eroded far inland is carried downstream and eventually deposited where river water slows. Over time, this sediment can build deltas and extend land outward. In other areas, strong currents remove more material than rivers supply, causing coastlines to retreat. The balance between addition and removal is never permanent. Because of these processes, no coastline remains the same indefinitely. What appears solid and reliable is actually transitional. Shorelines migrate, sometimes slowly and sometimes more noticeably, depending on local conditions. Ancient coastlines can now be found far inland, preserved as geological markers of earlier sea levels. Likewise, areas that are underwater today may once have been dry land. Maps capture coastlines at a single moment in time. Earth itself does not pause for mapping. The boundaries between land and sea adjust continuously, responding to forces that operate over centuries and millennia. This gradual adjustment is part of the planet's broader pattern of change. Seen over long periods, coastlines are not borders but conversations between land and water. Each responds to the other, shaping and reshaping the edge between them. The result is a surface that is never finished, only temporarily arranged. Through this slow interaction, Earth reminds us that even its most familiar outlines are provisional. The planet does not preserve shapes for their own sake. It allows them to shift, soften, and reform as conditions change, maintaining its steady rhythm of quiet transformation. Over long periods of time, Earth's climate has never remained fixed. It has shifted gradually between colder and warmer states, shaping landscapes, oceans, and living systems without abrupt turns. These changes emerge from steady interactions among Earth's orbit, its atmosphere, its oceans, and the surface below, each responding to small influences that accumulate across immense spans of time. One driver of long-term climate change is the way Earth moves through space. The shape of its orbit varies slightly, altering the total amount of sunlight received during different parts of the year. The tilt of Earth's axis also changes within a narrow range, redistributing sunlight between the equator and the poles. In addition, the orientation of that axis slowly turns, adjusting the timing of seasons relative to Earth's position around the sunday. None of these motions acts alone, and none produces dramatic effects in a single year. Their influence becomes clear only when their small differences persist for thousands of years. As these orbital patterns shift, ice responds. During cooler intervals, ice sheets expand across land, storing large amounts of water and brightening Earth's surface. Brighter surfaces reflect more sunlight back into space, reinforcing cooler conditions. During warmer intervals, ice retreats, darker land and ocean surfaces absorb more sunlight, and additional warming follows. This exchange between ice and sunlight unfolds gradually, allowing climate to move steadily rather than abruptly. Oceans provide another layer of moderation. Water absorbs heat efficiently and releases it slowly, smoothing temperature changes over time. Ocean currents transport warmth from low latitudes toward higher ones, influencing regional climates far from the tropics. When circulation patterns adjust, the redistribution of heat changes as well. These adjustments develop over long periods, guided by density, salinity, and the slow movement of water through deep basins. The atmosphere changes at its own pace. Gases that influence heat retention accumulate or diminish over extended intervals, altering how much energy remains near the surface. Because the atmosphere interacts continuously with oceans, ice, land, and life, changes rarely occur in isolation. Each adjustment feeds back into the broader system, nudging conditions in one direction or another without sudden leaps. Across Earth's history, climate transitions show continuity. Even major shifts unfolded step by step, guided by persistent forces rather than single triggers. Cooling phases deepened gradually. Warming phases emerged through long sequences of small changes. The absence of sharp boundaries reflects the way Earth balances energy over time. Seen together, these processes reveal climate as an expression of ongoing motion rather than a static background. The same patience that shapes mountains and coastlines governs the rise and retreat of ice and the slow rearrangement of atmospheric patterns. Climate follows rhythms set by accumulation and response, extending far beyond individual moments. Over deep time, this steady behavior allows Earth to remain dynamic without becoming unstable. Change proceeds through persistence, moderation, and balance. The planet adjusts continuously, guided by forces that favor gradual transformation over sudden shifts, maintaining a climate system shaped by time itself. Geological records preserve this slow pacing with remarkable clarity. Layers of sediment, chemical signatures in ice, and fossils embedded in rock capture gradual transitions rather than sharp breaks. These records show temperatures rising and falling in long arcs, sea levels advancing and retreating, and ecosystems adjusting their ranges in response. The evidence emphasizes duration, with trends unfolding across many generations, shaped by persistence more than intensity. Taken together, orbital motion, ice behavior, ocean circulation, and atmospheric composition form a connected system that resists sudden change. Each component responds to others with delay, spreading influence across time. This lag is essential, because it dampens extremes and favors continuity. Climate therefore evolves through accumulation and release, guided by small imbalances that persist. Over long spans, these imbalances redirect energy flows, reshape environments, and set the conditions under which life adapts. This pattern explains why climate history appears smooth when viewed broadly, even though local conditions vary. Gradual forcing allows systems to respond without breaking, maintaining coherence as circumstances change. The result is a climate shaped by time, memory, and interaction, advancing through steady adjustment rather than abrupt reversal. In this way, climate change reflects patience built into planetary motion, unfolding at a pace defined by accumulation and balance rather than immediacy across enduring spans of geological time. As climate shifts slowly, life responds on its own long timelines. Plants, animals, and entire ecosystems adjust through movement, adaptation, and gradual change across generations. These responses are rarely sudden. They emerge as conditions persist, allowing living systems to reorganize themselves without sharp breaks. When temperatures cool over long periods, ice expands and alters the distribution of water and land. Vegetation zones follow these changes. Forests withdraw toward regions that remain warmer or wetter, while grasslands and tundra extend into areas that once supported trees. As warming returns, the pattern reverses. Trees spread again, soils develop under new conditions, and ecosystems reorganize in place or through slow migration. Each shift unfolds across many lifetimes, guided by sustained conditions rather than brief events. Animals respond in similar ways. Populations gradually move to remain within suitable ranges of temperature and food availability. Over time, some species adapt physiologically or behaviorally to new environments. Others become restricted to smaller areas as conditions change around them. When pressure persists without relief, populations may decline and eventually disappear. Extinction in these cases reflects duration rather than sudden impact, the outcome of long exposure to limits rather than a single moment. Life does not only respond to climate, it also influences it. Vegetation affects how water moves through landscapes, how much sunlight is absorbed at the surface, and how carbon is exchanged with the atmosphere. Forests moderate temperatures locally by providing shade and releasing moisture. Grasslands reflect light differently and interact with wind in distinct ways. Over long periods, these effects contribute to broader environmental patterns. Soils record this interaction clearly. As plants establish themselves, they stabilize ground, retain moisture, and promote the formation of fertile layers. As climates shift, soil development changes with them, altering what kinds of plants can grow and how nutrients circulate. These feedbacks unfold slowly, reinforcing continuity rather than abrupt transition. Ecosystems therefore change through overlap rather than replacement. New communities emerge while older ones contract. Transitional zones expand and persist for long periods, blending characteristics of different environments. This gradual overlap allows life to adjust without requiring sharp boundaries between states. Across Earth's history, these patterns repeat. Life spreads when conditions allow and retreats when they do not, guided by persistence rather than urgency. Even large reorganizations of ecosystems reflect accumulated responses over time. The pace of biological change mirrors the pace of the planet itself. Viewed across deep time, stability in nature is temporary. What appears fixed within a human lifetime is often transitional when seen across thousands of years. Forests, deserts, wetlands, and grasslands all represent moments within longer sequences of change. Their forms reflect ongoing adjustment rather than permanence. This slow responsiveness gives life resilience. By operating on extended timescales, ecosystems absorb variation without collapsing. Change is distributed across space and time, allowing continuity even as conditions evolve. In this way, life remains closely tied to the rhythms of climate, responding steadily, reshaping environments as it adapts, and maintaining balance through gradual transformation. One of the quiet systems that shapes Earth over long periods is the movement of carbon through the planet. Carbon does not remain in one place or form. It circulates among air, water, living organisms, and solid rock, following pathways that operate at very different speeds. Some exchanges happen within years or decades. Others unfold across millions of years. Together, they form a slow circulation that influences climate, landscapes, and life without drawing attention to itself. In the atmosphere, carbon is present mainly as carbon dioxide. Plants absorb this gas as they grow, using it to build leaves, stems, and roots. As plants die or are consumed, some of that carbon returns to the air, while some becomes part of soils. Microorganisms break down organic material gradually, releasing carbon step by step rather than all at once. This steady exchange links living growth to atmospheric conditions. Oceans absorb large amounts of carbon as well. Carbon dioxide dissolves into seawater and becomes part of a complex chemical balance. Marine organisms use dissolved carbon to form shells and skeletal structures. When these organisms die, some of their remains sink toward the seafloor. Over time, layers of sediment accumulate, burying carbon beneath newer material. Pressure and chemical change slowly transform these deposits into rock, locking carbon away for very long periods. This transfer from surface to solid earth happens gradually. It does not depend on rare events. It depends on persistence. Rainwater reacts with certain minerals in rock, allowing carbon to bind chemically and be carried by rivers to the ocean. There, it becomes part of sediments that eventually harden into stone. This pathway removes carbon from the atmosphere over extended spans, moderating long-term conditions rather than causing rapid change. Carbon also returns from Earth's interior. As rock moves downward through tectonic processes, it carries carbon with it. Over immense timescales, this material is heated and altered. Volcanic activity releases some of this stored carbon back into the atmosphere. While individual eruptions may appear sudden, the overall release is slow when averaged across geological time. It represents the return leg of a cycle that has been unfolding since early in Earth's history. What defines this system is balance rather than control. No single pathway dominates permanently. When one process becomes more active, others respond gradually. Changes ripple through the system with delay, spreading influence across time. This delay is important. It prevents rapid swings and allows conditions to adjust steadily. The carbon cycle also links living systems to the physical planet. Life influences how carbon moves, and carbon availability influences how life develops. Vegetation alters soils and water flow, shaping how carbon is stored or released. Marine ecosystems affect how much carbon is transferred to sediments. These interactions develop slowly, reinforcing continuity rather than abrupt change. Across deep time, the movement of carbon helps explain why Earth's climate has remained responsive without becoming unstable. By operating on long timescales, the cycle spreads change across many generations. Adjustments accumulate gradually, shaping temperature patterns, ocean chemistry, and the conditions under which ecosystems persist. When viewed broadly, the carbon cycle is less a loop than a circulation with memory. Carbon that moves today may not return to the surface for millions of years. This long residence time anchors Earth's behavior, favoring gradual transformation over sudden shifts. The planet adjusts through accumulation and release, guided by pathways that value persistence. In this way, carbon acts as a quiet mediator between rock, water, air, and life. Its slow movement ties together processes that would otherwise seem separate. Over long spans, this mediation shapes climates, supports ecosystems, and maintains continuity. The changes it produces are rarely immediate, but they are enduring, unfolding at a pace set by time itself. Life on Earth has never been a passive passenger. From its earliest forms, living organisms have interacted with the planet in ways that slowly but persistently reshaped surface conditions. Over long spans of time, life altered the chemistry of the atmosphere, the structure of soils, and the flow of energy across the surface. These changes did not happen quickly, and they did not follow a single direction. They emerged through accumulation, as biological processes repeated themselves across countless generations. One of the most significant shifts began when early microorganisms started using sunlight to drive their metabolism. In doing so, they released oxygen as a byproduct. At first, this oxygen reacted with minerals and dissolved substances, leaving little trace in the air. Over time, as these reactions reached their limits, oxygen began to accumulate in the atmosphere. This gradual build-up transformed surface conditions, allowing new forms of life to emerge and altering how energy moved through the environment. Plants later expanded this influence. By absorbing carbon dioxide and releasing oxygen, vegetation became a major participant in atmospheric balance. Forests, grasslands, and other plant communities changed how much sunlight the surface absorbed, how moisture circulated, and how heat was retained or released. These effects developed slowly, shaped by the spread of vegetation across continents and the persistence of growth over long periods. Life also reshaped the land itself. Roots broke apart rock, allowing soil to form where bare stone once dominated. Organic material accumulated, increasing fertility and altering how water moved through the ground. As soils deepened, they supported more complex ecosystems, reinforcing the connection between life and surface conditions. Each layer formed through repetition rather than speed, building structure through time. In the oceans, living organisms played a similar role. Microscopic life influenced water chemistry by absorbing and releasing elements as part of their growth. Shell-building organisms removed dissolved carbon from seawater, contributing to the formation of sediments that later became rock. Coral structures grew slowly, shaping coastlines and influencing ocean currents over extended spans. These biological contributions accumulated quietly, altering marine environments without sudden transitions. Life also influenced climate indirectly through feedbacks. Vegetation affects evaporation, cloud formation, and regional rainfall patterns. Large ecosystems modify wind flow and surface temperatures, creating local conditions that persist over time. These effects are subtle when viewed year by year, yet they become significant when sustained across centuries and longer intervals. What stands out in these interactions is reciprocity. Life responds to environmental conditions, but it also modifies those conditions in return. This mutual influence does not lead to immediate equilibrium. Instead, it creates ongoing adjustment, with biological and physical systems responding to one another through delay and persistence. Across Earth's history, these interactions have allowed life to remain intertwined with planetary processes. Atmosphere, soil, ocean, and climate have all been shaped in part by living activity. The influence is cumulative rather than dramatic, unfolding through repetition rather than force. Seen across deep time, life becomes one of Earth's shaping agents. Its impact lies not in rapid change, but in continuity. By acting steadily and persistently, living systems help guide how the planet evolves. The result is a surface and atmosphere marked by biological presence, adjusted gradually through time, and shaped by the quiet persistence of life itself. Extinction and renewal are often imagined as dramatic turning points, yet across Earth's long history they usually unfold through gradual pressure rather than sudden collapse. Species rarely disappear because of a single moment. More often, they decline as conditions shift beyond what they can tolerate, narrowing ranges and reducing numbers over many generations. This slow erosion of suitability shapes biological change just as steadily as uplift and erosion shape the land. As climates adjust and environments reorganize, habitats move, forests retreat or advance, shorelines shift, and temperature zones migrate across latitudes and elevations. Species tied closely to specific conditions must follow these changes to persist. Some succeed by moving gradually with their preferred environment. Others adapt over time, adjusting behavior, physiology, or life cycles. When neither movement nor adaptation keeps pace with persistent change, populations diminish. These declines are rarely uniform. A species may vanish from large areas while surviving in isolated regions where conditions remain favorable. Over long periods, fragmentation reduces genetic diversity and resilience. The process is quiet and extended, marked by fewer individuals and narrower ranges rather than sudden absence. Extinction, in this sense, reflects duration and accumulation rather than immediacy. Renewal follows a similar rhythm. As older forms decline, opportunities open for others. Empty niches allow surviving species to expand or diversify. Over many generations, small variations become established, giving rise to new forms better suited to prevailing conditions. This emergence is incremental, guided by persistence rather than speed. The result is a gradual reshaping of ecosystems rather than abrupt replacement. Geological records capture this pattern with clarity. Fossil layers often show overlapping presences rather than sharp boundaries. Groups decline while others rise, with long intervals of coexistence. Even large reorganizations of life reflect extended transitions, shaped by sustained pressures and delayed responses. The continuity of these records emphasizes process over event. Life's resilience lies in this gradualism. By spreading change across time, ecosystems absorb pressure without immediate failure. Diversity provides options, allowing some lineages to persist while others fade. Over deep time, this balance between loss and emergence maintains complexity without stasis. Extinction and renewal also interact with the physical planet. As vegetation patterns change, soils develop differently. As marine communities shift, sediment composition alters. These biological adjustments feed back into surface conditions, influencing how landscapes and oceans evolve. The connection reinforces continuity, with living and non-living systems adjusting together. Viewed broadly, extinction is not an endpoint, but part of an ongoing sequence. Renewal does not erase what came before. It builds upon the conditions left behind. Together, they describe a long rhythm of contraction and expansion, guided by persistence. Across Earth's history, this rhythm has allowed life to continue despite changing circumstances. Species come and go, but life remains woven into planetary processes. The pace is measured, the transitions extended, change unfolds through accumulation, maintaining continuity even as forms transform across enduring spans of time. Volcanoes are often remembered for their eruptions, yet their deeper significance lies in the slow processes that make those moments possible. Long before molten rock reaches the surface, heat and material move gradually within Earth's interior. This movement is patient and continuous, guided by density, pressure, and the transfer of energy from deeper layers toward the crust. Deep below the surface, rock becomes hot enough to soften and partially melt. This material does not surge upward. It rises slowly where conditions allow, collecting in pockets and chambers beneath the crust. Over long periods, pressure builds as new material arrives and gases accumulate. Most of this activity remains hidden, unfolding without visible signs at the surface. When an eruption finally occurs, it represents the release of pressure that has been building for a very long time. The event itself may be brief, but it reflects an extended history of internal motion. Once material is released, the system settles again, returning to its slow pace. New rock cools and solidifies, becoming part of the surface landscape. Over time, repeated eruptions can build mountains, plateaus, and islands, layer by layer. Volcanic activity also plays a role in shaping Earth's atmosphere and oceans. Gases released from molten rock contribute to atmospheric composition, influencing how heat is retained near the surface. Over geological time, these slow emissions help regulate long-term conditions rather than cause immediate change. The effect emerges through accumulation rather than intensity. On land, volcanic material weathers into mineral-rich soils. These soils often support dense vegetation once conditions stabilize, linking deep earth processes to surface ecosystems. In the oceans, volcanic activity creates new seafloor, providing fresh surfaces for chemical exchange and biological colonization. Each contribution develops gradually, reinforcing continuity between interior motion and surface life. What distinguishes volcanic systems is their balance between quiet preparation and brief release. Earth spends far more time moving material beneath the surface than displaying it above. This balance prevents sudden exhaustion of internal energy, allowing activity to persist across billions of years. Viewed across deep time, volcanoes are not interruptions but participants in Earth's long rhythm. They recycle material, redistribute energy, and connect the planet's interior to its surface. Their influence is steady when measured over long spans, shaping landscapes and conditions through repetition rather than force. In this way, volcanic activity reflects Earth's preference for gradual transformation. Change arises through sustained motion, guided by pressure and release, maintaining a system that remains active without rushing toward resolution. Earth is surrounded by a magnetic field that is invisible yet essential, and like many other planetary systems, it changes slowly over time. This field is generated deep within the planet, far below the surface, where molten material moves within the outer core. The motion of this electrically conductive fluid creates a vast magnetic envelope that extends outward into space. Although the field feels stable in everyday life, it is the product of continuous internal motion rather than a fixed structure. The generation of the magnetic field depends on heat and movement. As Earth's interior slowly releases energy, material in the outer core circulates. This circulation does not follow a simple or permanent pattern. Flow paths shift gradually as conditions change, altering the strength and orientation of the magnetic field above. These changes are subtle and unfold over long periods, often spanning thousands of years. One expression of this slow adjustment is the wandering of the magnetic poles. The locations where the field appears strongest drift gradually across the surface. This movement is irregular but steady, reflecting changes deep within the planet rather than events at the surface. Compasses respond to these shifts over time, adjusting to a field that is always in motion even when it feels constant. Over much longer spans, the magnetic field can weaken and eventually reverse its orientation. These reversals do not happen suddenly. The field becomes disordered for extended intervals before settling into a new configuration. Geological records preserved in volcanic rock show this process clearly. As lava cools, minerals align with the magnetic field present at the time, recording its direction. Stacked layers reveal gradual transitions rather than abrupt switches. The magnetic field also interacts with space beyond Earth. It deflects charged particles from the sun, shaping how energy enters the upper atmosphere. This interaction influences atmospheric chemistry and helps protect surface conditions over long periods. Changes in field strength alter this shielding slightly, but the effects emerge gradually, integrated across time rather than felt as immediate shifts. What stands out is continuity. Even as the magnetic field changes, it remains present. Its behavior reflects the same balance seen in other Earth systems, where internal motion leads to slow adjustment rather than instability. The field does not seek a fixed state. It responds continuously to the movement within the planet. Seen across deep time, Earth's magnetism becomes another expression of internal energy finding balance. It links the deep interior to the space around the planet, translating slow motion below into subtle influence above. The result is a system that evolves patiently, shaped by persistence rather than speed. Through this gradual change, the magnetic field mirrors the broader character of Earth itself. It is active without being abrupt, dynamic without being chaotic, and sustained through time by steady motion deep within the planet. Earth's motion through space is steady, yet even this motion is not perfectly fixed. Over long periods, the planet's rotation and orientation adjust gradually under the influence of gravity. These changes are subtle, unfolding far too slowly to notice in daily life, but across deep time, they contribute to the shifting patterns of seasons, climate, and long-term stability. Earth rotates on its axis, creating the cycle of day and night. This rotation is not constant at every scale. Tidal interactions with the Moon and, to a lesser extent, the Sun apply gentle friction to the planet. Over immense spans of time, this friction slows Earth's rotation by small amounts. The length of a day increases so gradually that it becomes meaningful only when measured across millions of years. The planet does not stop spinning, it simply adjusts its pace through continuous interaction. At the same time, Earth's axis is tilted relative to its orbit around the Sunday. This tilt gives rise to seasons by changing how sunlight is distributed throughout the year. The angle of this tilt is not perfectly stable. It varies slowly within a limited range, altering the contrast between seasons over long periods. When the tilt increases, seasonal differences become more pronounced. When it decreases, seasons grow milder. These shifts develop gradually, blending into broader climate patterns. The orientation of Earth's axis also changes through a slow turning motion. This alters the timing of seasons relative to Earth's position in its orbit. The result is not sudden disruption, but subtle redistribution of sunlight across hemispheres and latitudes. When combined with changes in orbit and tilt, this motion contributes to long-term cycles in climate. These adjustments do not act in isolation. They interact with oceans, ice, and the atmosphere, influencing how energy is stored and released. A slight change in sunlight distribution can alter ice coverage, which then affects reflectivity and temperature. The response unfolds over extended intervals, shaped by feedbacks that favor continuity rather than abrupt change. What emerges from these interactions is moderation. Earth's motion evolves in ways that distribute influence across time, preventing sudden extremes. The planet responds through accumulation and delay, allowing systems to adapt gradually. Rotation, tilt, and orientation form part of a larger balance that supports long-term stability without requiring stillness. Viewed across deep time, Earth's movement becomes another example of persistence shaping outcome. Small gravitational influences, repeated endlessly, produce measurable change. The pace remains slow, the direction steady. Through this ongoing adjustment, Earth maintains a rhythm that supports continuity, allowing surface conditions to evolve without breaking the broader system. Soil is often taken for granted, yet it is one of the clearest records of Earth's slow transformation. It forms through the gradual breakdown of rock, guided by water, temperature, chemistry, and living activity. This process does not hurry. It unfolds grain by grain, creating the thin layer that supports forests, grasslands, and agriculture only after long periods of steady change. The formation of soil begins with weathering. Physical forces break rock into smaller pieces as temperatures rise and fall, causing expansion and contraction. Water enters tiny cracks, widening them over repeated cycles. Chemical reactions alter minerals at the surface, weakening their structure and making them easier to fragment. Each of these actions removes only a small amount of material, but they continue without pause. As rock fragments become finer, they mix with organic material produced by living organisms. Plants contribute leaves, roots, and other remains that decompose slowly. Microorganisms break this material down further, releasing nutrients and altering soil chemistry. Over time, These processes create layers with distinct properties, reflecting long histories of interaction between rock, water, air, and life. Soil development responds closely to climate. In wetter conditions, chemical weathering proceeds more rapidly, producing deeper soils with well-defined layers. In drier or colder regions, soil forms more slowly and remains thinner. These differences do not appear suddenly. They emerge through persistence, with climate guiding the pace and character of formation over extended spans. Movement also plays a role. Gravity carries loosened material downhill, redistributing soil across slopes and valleys. Rivers transport fine particles, depositing them on floodplains where fertile soils gradually accumulate. Wind moves dust across continents, contributing material far from its original source. Each pathway operates quietly, spreading influence across space and time. Soils are not permanent. They erode, compact, and change composition as conditions shift. Vegetation patterns influence how well soil is retained, while climate affects moisture and chemical balance. When environments change, soil responds slowly, altering its structure and nutrient content over long periods. Seen across deep time, soil represents continuity rather than completion. It forms, adjusts, and reforms as landscapes evolve. The presence of fertile ground reflects countless small changes accumulated patiently. Through this gradual process, soil connects Earth's interior rock to surface life, supporting ecosystems by providing a stable yet responsive foundation shaped by time. Earth's large environments often appear permanent. Deserts seem destined to remain dry, forests seem rooted in place, and oceans appear fixed in their boundaries. Yet these environments are temporary arrangements within a much longer sequence of change. Over deep time, deserts become grasslands, forests give way to open plains, and seas advance or retreat as conditions slowly shift. Climate plays a central role in these transformations. Gradual changes in temperature and precipitation alter how water moves through the landscape. Regions that receive less moisture over long periods lose vegetation and soil, allowing dry environments to expand. Where rainfall increases and temperatures moderate, plant life slowly returns, stabilizing ground and reshaping local climates. These transitions do not happen abruptly. They develop through persistence, as conditions remain favorable or unfavorable across many generations. Tectonic movement also reshapes environments. As land rises or sinks, patterns of drainage and rainfall adjust. Mountain ranges influence wind flow, redirecting moisture and creating rain shadows that alter ecosystems on either side. Over long spans, these effects shift the boundaries between forests, grasslands, and deserts. The changes are subtle from year to year, but they accumulate steadily. Oceans, too, reflect gradual transformation. Sea levels rise and fall as ice volume changes and as the ocean floor slowly moves. Shallow seas may cover continents during warmer intervals, supporting marine life where land once existed. When seas retreat, exposed ground weathers and develops new soils. These cycles leave layered records in rock, marking transitions between marine and terrestrial environments. Living organisms respond to these shifts and contribute to them. Vegetation alters evaporation and surface temperature, reinforcing environmental conditions. Marine life influences sediment formation and water chemistry. Over time, these biological effects interact with physical changes, guiding how environments evolve. What defines these transformations is overlap rather than replacement. Old environments contract, while new ones expand. Transitional zones persist for long periods, blending characteristics of both. This overlap allows ecosystems to reorganize gradually, rather than collapse. Seen across Earth's history, no environment is final. Each represents a moment within a longer flow of change. The planet does not preserve landscapes for their own sake. It allows them to adjust as conditions evolve, maintaining continuity through gradual transformation rather than sudden shift. The sun provides the energy that drives nearly all surface activity on Earth, yet its influence is expressed through slow and steady interaction rather than constant intensity. While the Sun itself changes gradually over very long periods, Earth's systems respond to its energy through layers of moderation that spread influence across time. This relationship shapes climate, weather patterns, and the distribution of life without producing abrupt shifts. Sunlight reaches Earth unevenly. The angle at which it arrives varies with latitude, season, and long-term orbital patterns. Regions near the equator receive more consistent energy, while higher latitudes experience stronger seasonal contrasts. Over long periods, small changes in how sunlight is distributed alter temperature gradients across the planet. These gradients guide atmospheric circulation, influencing wind patterns and precipitation zones that persist for centuries. Earth's surface responds differently depending on what it absorbs. Dark surfaces such as oceans and forests take in more solar energy, warming gradually and storing heat. Lighter surfaces such as ice and desert sands reflect more sunlight, reducing absorption. As environments change, the balance between absorption and reflection shifts. These adjustments unfold slowly, reinforcing trends already in motion rather than creating sudden reversals. Oceans play a central role in mediating solar influence. Water absorbs heat efficiently and releases it slowly, smoothing temperature variation over time. Large currents transport this stored warmth across vast distances, distributing solar energy from regions of surplus to regions of deficit. Changes in these circulation patterns develop gradually, guided by density differences and the steady flow of water through deep basins. The atmosphere responds through circulation and chemistry. Air masses move heat from warmer to cooler regions, while gases influence how much solar energy remains near the surface. Variations in solar input interact with these atmospheric processes, producing long-term patterns rather than immediate change. Each adjustment feeds back into the system with delay, favoring continuity. Life responds to this steady solar rhythm as well. Photosynthesis depends on consistent light availability, and ecosystems organize around long-term energy patterns. Shifts in sunlight distribution influence growing seasons, vegetation zones, and migration routes over extended spans. Seen across deep time, the sun's role is one of steady guidance rather than control. Its energy sets the conditions within which Earth's systems operate, but those systems respond through accumulation and moderation. Change unfolds through persistence, shaped by the slow interaction between incoming energy and the planet's capacity to absorb, store, and redistribute it. Over Earth's long history, continents have not remained isolated or fixed in their positions. Instead, they have repeatedly gathered together into large landmasses and later separated again. This slow cycle of assembly and breakup unfolds across hundreds of millions of years, driven by the steady movement of tectonic plates beneath the surface. When continents drift toward one another, ocean basins gradually narrow, seafloor is recycled back into the mantle, and landmasses begin to collide. These collisions do not produce immediate outcomes. They develop slowly, compressing crust and altering elevation over extended periods. Vast interior regions form as continents merge, reshaping climate patterns by changing how air and moisture move across the surface. Large land masses influence temperature and rainfall by creating distance from the ocean. Interior regions tend to become drier and experience greater seasonal variation, while coastal areas retain more moderate conditions. Over long spans, these patterns guide the distribution of ecosystems, favoring some forms of life while limiting others. The biological response unfolds gradually, shaped by sustained conditions rather than sudden change. As tectonic forces continue, stress builds within the merged continents. Heat accumulates beneath thickened crust, and fractures begin to form. Slowly, the landmass weakens and starts to separate. New rifts open, allowing magma to rise and solidify into fresh crust. Over immense periods, narrow rifts widen into oceans, dividing continents that were once joined. These cycles leave clear records in rock, matching geological formations, fossil distributions, and mineral deposits appear on continents now separated by oceans, revealing their shared history. The evidence shows continuity rather than abrupt transition, with assembly and breakup unfolding through long sequences of motion. What stands out is repetition. No configuration lasts forever. Continents gather, alter climate and life, then disperse again. Each cycle reshapes the planet's surface and influences how energy and matter circulate. Seen across deep time, continental cycles reflect Earth's tendency toward gradual reorganization. The planet does not preserve arrangements indefinitely. It allows them to evolve through persistence, maintaining balance by redistributing land and sea over extended spans. Sea level has never been fixed throughout Earth's history. Instead, it has risen and fallen gradually as ice volumes, temperatures, and the shape of the ocean floor have changed over long periods of time. These shifts do not reflect sudden instability. They emerge through accumulation, guided by slow adjustments in climate and tectonic movement. One influence on sea level is the amount of water stored as ice on land. During cooler intervals, large ice sheets expand across continents, holding vast quantities of water that would otherwise be in the oceans. As ice grows, global sea level slowly falls. During warmer intervals, ice retreats, releasing water back into the oceans. This process unfolds over thousands of years, allowing coastlines to migrate gradually rather than abruptly. The oceans themselves respond to temperature. As water warms, it expands slightly. When temperatures cool, it contracts. These changes are subtle, yet when sustained across long periods, they influence sea level noticeably. Thermal expansion does not act alone. It interacts with ice volume and circulation patterns, spreading influence across time. Tectonic activity also shapes sea level by altering the capacity of ocean basins. As seafloor spreads at mid-ocean ridges, it displaces water, raising sea level slowly. When spreading slows and older seafloor cools and sinks, ocean basins deepen, allowing sea level to fall. These adjustments develop over millions of years, guided by the same internal processes that move continents. Local conditions vary as well. Land can rise or sink due to tectonic forces, sediment accumulation, or erosion. A coastline may experience relative sea level change, even when global levels remain stable. Over long periods, these local movements shape where shorelines persist and where they retreat, leaving records in terraces, sediments, and rock formations. Geological layers preserve these slow changes clearly. Marine sediments found far inland mark times when seas-covered areas now dry. Fossil reefs elevated above current shorelines reveal former sea levels. These records show progression rather than abrupt jumps, reflecting the pace at which conditions shifted. Across deep time, sea level change illustrates continuity. Water advances and retreats as conditions evolve, reshaping coastlines and shallow seas gradually. The movement is steady, guided by long-term balance between ice, temperature, and the structure of the ocean floor. In this way, sea level reflects Earth's preference for gradual adjustment, unfolding through persistence rather than sudden transition. Small changes often appear insignificant when viewed in isolation. A slight shift in temperature, a minor adjustment in elevation, or a slow change in water flow may seem too subtle to matter. Yet across Earth's history, it is precisely these small and repeated changes that have produced the largest transformations. The planet evolves through accumulation, with tiny adjustments building upon one another over immense spans of time. When rock is lifted by tectonic forces, the movement in any single year is almost imperceptible. At the same time, erosion removes a similarly small amount of material from the surface. Each action alone appears minor. Together, and sustained over millions of years, they determine the height and shape of entire mountain ranges. The balance between addition and removal shapes landscapes not through force, but through persistence. Climate follows the same pattern. A slight redistribution of sunlight alters temperature by a small amount. That change affects ice, vegetation, and ocean circulation in subtle ways. Each response feeds back into the system, reinforcing or moderating the original shift. Over long periods, these layered responses lead to substantial reorganization. The result is not sudden transformation, but a new equilibrium reached through gradual steps. Rivers illustrate accumulation clearly. Each grain of sediment they carry represents a tiny change to the land. Over time, these grains carve valleys, build deltas, and reshape continents. No single moment defines the outcome. The landscape reflects the sum of countless small movements rather than any single event. Biological systems respond in similar fashion. Slight advantages in survival or reproduction, when sustained across generations, lead to noticeable shifts in populations. Ecosystems reorganize as conditions persist, allowing some forms to expand and others to retreat. The pace remains slow, guided by continuity rather than urgency. These examples share a common feature. Earth does not rely on dramatic episodes to change its form. It depends on repetition. Processes repeat under stable rules, allowing effects to build gradually. This repetition provides coherence, preventing abrupt collapse while enabling long-term transformation. Across deep time, accumulation becomes the dominant force. The planet's surface, climate, and living systems all reflect the outcome of sustained adjustment. What appears stable in the present moment is often the temporary result of long-running processes still in motion. Seen this way, Earth's history is not a sequence of disruptions, but a continuous flow shaped by persistence. Small changes matter because they endure. Through accumulation, the planet reshapes itself patiently, maintaining continuity while allowing transformation to unfold over enduring spans of time. When Earth's long history is viewed as a whole, human presence occupies only a very brief interval. This perspective does not diminish human experience, but it places it within a much larger context shaped by processes that began long before people appeared. The planet had already formed mountains, oceans, climates, and ecosystems through slow change when humans first emerged. Human societies developed during a relatively narrow window of environmental conditions. Stable coastlines, predictable seasons, and established ecosystems allowed agriculture to develop and settlements to persist. These conditions were not permanent features of Earth. They were the result of long sequences of adjustment that happened to align in ways favorable to human activity. The stability experienced within recorded history reflects a moment within deeper planetary motion rather than an enduring state. As humans spread across the surface, they interacted with existing systems shaped by long processes. Rivers had already carved valleys. Soils had already formed through extended weathering. Climate patterns had been established through slow interaction between orbit, atmosphere, and oceans. Human activity took place within these structures rather than creating them from nothing. Over time, human actions began to influence local environments. Land was cleared, water was redirected, and species were moved between regions. These changes unfolded over centuries, not moments, and they interacted with natural systems already in motion. The planet continued to respond through the same mechanisms that shaped it previously, adjusting gradually to new conditions rather than breaking from its long patterns. What stands out is scale. Human timelines measure progress in years and generations, while Earth's systems respond across much longer spans. Effects that seem rapid within human history are often absorbed slowly by geological and ecological processes. The planet integrates new influences through accumulation, spreading change across time. Seen across deep time, humanity becomes one participant among many in Earth's ongoing transformation. The presence of people does not interrupt the planet's processes. It becomes part of them. Landscapes continue to evolve, climates continue to adjust, and ecosystems continue to reorganize under the influence of forces acting at multiple scales. This perspective emphasizes continuity rather than separation. Earth does not distinguish between natural and human influence in its long record. It responds to all inputs through the same patient mechanisms. Change unfolds through persistence, guided by accumulation rather than immediacy. Placed within Earth's broader story, human history appears as a brief chapter within a much longer narrative. The planet's slow rhythm continues, shaped by forces that extend far beyond any single era, maintaining continuity while allowing new forms of influence to be absorbed over time. Human activity now interacts with Earth's slow systems in ways that occur on shorter timescales, yet the planet responds through the same long mechanisms that have always shaped it. Energy, materials, and landscapes adjust gradually, absorbing new influences through processes that distribute change across time, rather than concentrating it in a single moment. When materials are added or removed at the surface, Earth does not react instantly. Rivers adjust their courses over years and decades. Soils respond as layers are altered, compacted, or replenished. Vegetation reorganizes as conditions persist, spreading or retreating across landscapes through gradual movement. These responses reflect continuity rather than interruption, guided by persistence instead of immediacy. Atmospheric changes also follow this pattern. Gases mix globally, spreading influence rather than remaining localized. Oceans absorb heat and substances slowly, releasing them over extended periods. The delay inherent in these systems moderates change, allowing adjustments to unfold through accumulation. Even when inputs increase, responses are distributed across time by storage and circulation. The interaction between human activity and natural cycles therefore becomes one of timing rather than dominance. Processes that normally operate slowly continue to do so, integrating new conditions through existing pathways. Carbon exchanges follow established routes. Water cycles respond according to gradients and flow. Energy moves through atmosphere and ocean with delay, maintaining continuity. Landscapes show this integration clearly. Areas altered by sustained use gradually develop new forms of stability. Riverbanks reshape, soils evolve, and vegetation adapts to repeated conditions. These changes do not erase prior structure immediately, they layer upon it, producing outcomes that reflect both past and present influences. What remains consistent is Earth's method. The planet absorbs variation by spreading it across space and time. Feedbacks soften extremes, while persistence allows patterns to emerge. This approach prevents rapid collapse and favors gradual reorganization. Seen across deep time, the interaction between human activity and Earth systems fits within the planet's broader behavior. New influences are not isolated. They become part of the same cycles that have guided change for billions of years. The pace may differ, but the mechanisms remain steady. Through this lens, Earth continues its slow transformation. It responds to added influences through accumulation, moderation, and delay. The surface evolves, climates adjust, and ecosystems reorganize without abandoning continuity. Change proceeds through persistence, maintaining the planet's long rhythm while incorporating new conditions over time. Earth does not move toward a fixed or ideal state. Stability, when it appears, is temporary. The planet functions through continuous adjustment, responding to internal motion and external influence without settling into permanence. Balance emerges not as stillness, but as ongoing correction, where forces counteract one another over long periods of time. This dynamic balance can be seen across Earth's systems. Tectonic movement raises land while erosion lowers it. Heat rises from the interior while the surface releases energy into space. Ice expands and reflects sunlight while darker surfaces absorb it. None of these processes aims for completion. Each responds to conditions as they persist, guiding gradual change rather than abrupt resolution. Climate reflects this pattern clearly. Temperature does not hover around a single value indefinitely. It shifts within ranges defined by orbital motion, atmospheric composition, and surface feedbacks. When one influence strengthens, others respond with delay, moderating extremes. The result is movement within boundaries rather than drift toward a final condition. Living systems follow the same logic. Ecosystems expand, contract, and reorganize as environments change. No arrangement lasts indefinitely. Forests give way to grasslands, wetlands dry or reform, and marine communities adjust to shifts in chemistry and circulation. These changes are not failures of stability, they are expressions of balance in motion. Earth's surface records this ongoing adjustment. Mountain ranges rise and are worn down. Coastlines advance and retreat. Soils develop and erode. Each feature reflects a moment within longer processes still unfolding. What appears settled within a human lifetime is often transitional when viewed across deeper time. This absence of a final state allows resilience. By never locking into a single configuration, Earth remains capable of responding to change. Systems adapt gradually, distributing influence across time rather than concentrating it. Persistence replaces rigidity, allowing continuity without stasis. Seen across deep time, balance becomes a process rather than a goal. Earth maintains coherence by adjusting continuously, guided by interactions that unfold slowly. Change does not signal instability. It signals responsiveness built into the planet's behavior. Through this lens, Earth's history is not a march toward equilibrium, but an ongoing negotiation among forces. The planet remains active, flexible, and enduring because it never stops adjusting. Balance is maintained through motion, allowing Earth to evolve while preserving continuity across enduring spans of time. Studying Earth's slow changes alters how time itself is perceived. When attention shifts from immediate events to long processes, urgency fades and patterns become clearer. Change no longer appears as interruption, but as a continuous flow shaped by persistence. This perspective does not remove uncertainty. It reframes it as a natural feature of systems that unfold across extended spans. On long timescales, cause and effect are rarely direct. Small influences accumulate, interact, and sometimes counteract one another before producing noticeable outcomes. A minor shift in energy balance may take centuries to express itself fully. During that time, other processes continue, shaping the final result. Understanding emerges not from isolating single factors, but from observing how many forces combine gradually. This way of thinking emphasizes patience. Outcomes cannot be rushed, and predictions remain approximate because systems respond with delay. Earth's history shows that long processes rarely follow straight lines. They curve, pause, and redirect as conditions evolve. This does not indicate disorder. It reflects responsiveness within a complex framework. Perspective also broadens. Individual events become part of longer sequences rather than isolated moments. A single flood fits within patterns of river behavior shaped over thousands of years. A drought reflects climate tendencies that developed gradually. Seeing these connections reduces the emphasis on immediacy and highlights continuity. Scientific understanding benefits from this shift. Evidence gathered from rock layers, fossils, and chemical signatures gains meaning when placed within long timelines. Patterns that seem subtle in short records become clear when extended across deeper time. Knowledge grows through accumulation, much like the processes it describes. This approach does not eliminate uncertainty, but it makes room for it. Earth's systems are shaped by interactions that cannot be measured perfectly at every scale. Accepting gradual change allows space for adjustment, revision, and learning. Confidence comes not from exact prediction, but from recognizing stable patterns within variability. Seen across deep time, Earth teaches restraint. Large transformations arise from persistent influence rather than forceful action. Understanding develops through observation and repetition. The planet's history invites a slower pace of thought, one that values continuity and patience. Through this lens, learning about Earth becomes an exercise in alignment with its rhythm. Change unfolds steadily, guided by accumulation. By adopting a long view, the mind adjusts to processes that favor endurance over immediacy, reflecting the same principles that shape the planet itself. Earth's future is not a destination waiting to be reached. It is a continuation of processes already in motion, shaped by forces that have been active for immense spans of time. The same interactions that guided the planet's past continue to operate, carrying momentum forward without requiring a fixed outcome. Change proceeds through pathways established long before the present moment. Internal heat will continue to move through the planet, driving slow adjustments beneath the surface. Tectonic plates will keep drifting, opening and closing ocean basins over long intervals. Mountains will rise and be worn down. Rivers will continue to transport material from high ground to low. These processes do not depend on prediction or intention. They persist because the conditions that sustain them remain. Climate will also continue to adjust. Orbital motion, atmospheric composition, and ocean circulation will interact as they always have, redistributing energy gradually. Ice will expand and retreat as conditions allow. Sea levels will rise and fall over extended spans. These changes will not follow a straight path. They will reflect accumulation, delay, and feedback rather than simple progression. Life will remain intertwined with these developments. Ecosystems will reorganize as environments shift, with some forms expanding and others contracting. New arrangements will emerge gradually, shaped by persistence rather than speed. The interaction between living systems and physical processes will continue, reinforcing continuity between biology and geology. What remains consistent is Earth's method. The planet does not rush toward resolution, it adjusts through moderation, spreading influence across time and space. Even when conditions change, responses are distributed, allowing systems to adapt rather than break. Seen across deep time, the future becomes an extension of the present rather than a separate phase. Forces already at work will continue to shape outcomes, guided by balance rather than finality. Earth's story does not move toward completion. It unfolds. This perspective emphasizes continuity over certainty. The planet's future is not a single path, but a range of possibilities shaped by ongoing interaction. Change remains gradual, governed by the same rhythms that have guided Earth through its long history. In this way, the future mirrors the past. It is defined not by endpoints, but by motion. Earth continues to change because change is built into its structure, sustained by processes that favor persistence. The planet moves forward through steady adjustment, carrying its history with it as it evolves across enduring spans of time. Earth's story does not conclude with a final shape or lasting arrangement. What remains constant is the process itself. From the slow movement of rock deep below the surface to the quiet adjustment of climate, oceans, and life, the planet continues to reshape itself through persistence rather than force. Change unfolds not as a series of endings, but as a continuous flow. Across everything that has been explored, one pattern returns again and again. Earth does not hurry. It allows influences to accumulate, responses to unfold, and balance to emerge through time. Mountains rise while erosion lowers them. Ice advances and retreats. Forests spread and contract. Seas open and close. Each movement is small when viewed alone, yet powerful when sustained. This slow rhythm connects processes that might otherwise seem separate. Heat rising from the interior influences the surface. Sunlight shapes climate, which guides ecosystems. Life alters soil, air, and water, feeding back into the systems that support it. Nothing operates in isolation. Each part responds to others with delay, spreading change across generations and landscapes. What appears stable at one moment is often transitional when viewed across deeper time. Coastlines shift. Environments reorganize. Conditions that support one form of life gradually give way to others. These transitions are not abrupt. They overlap, blend, and extend, allowing continuity even as forms transform. Earth's ability to change slowly is what allows it to endure. By distributing influence across time, the planet avoids extremes and maintains coherence. Adjustment replaces rigidity. Persistence replaces urgency. The result is a system that remains active without becoming unstable. Seen in this way, Earth is never finished. It is always becoming something slightly different from what it was before. The surface reflects countless small adjustments layered upon one another, each leaving traces that guide what comes next. The planet carries its history forward, shaping future conditions through the same steady mechanisms that shaped the past. As these ideas settle, there is no need to resolve them into conclusions. Earth does not seek closure. It continues through motion, guided by balance and time. Change remains quiet, constant, and patient, unfolding beyond any single moment. We from Sleepy Stories wish you a good night.